Hello everyone, my name is Vinicius Mattoso, and the title of this work is Reservoir Characterization based on a transient pressure and temperature data using an ensemble-based method. This work is a preview of my master thesis at LMMP from PUC-Rio. It's advised by the Professor Márcio Carvalho and co-advised by the Dr. Damer Maza. The presentation starts with the contextualization of where our product fits in the oil and gas industry. The work is belong to the reservoir management area. This area has multiple divisions, and our products are inside the reservoir characterization. Here is an example of a well-born reservoir model where the well tests are commonly used to characterize the reservoir parameters and estimate the production potential of the field. Usually, those parameters are the permeability in different regions of the reservoir and the porosity. The data availability is essential for the reservoir characterization. Those data can come from different sources and from different times of production. In the work, the data will come from the well test before the production field start. The well test consists of the existing data during a control process of opening and close the production valve. In this flow plot here, you can understand better this works. When the valve is open, we are producing with this key flow rate, and as a consequence, the pressure starts to decrease until the valve is closed. When the valve is closed, the flow rate is zero and the pressure starts to recover its initial condition. With the use of the advanced data analysis technique, the quality of the reservoir parameter estimate has increased, contributing to a better production plan of the field. The pressure data are commonly used, but due to the advanced well sense, the temperature sensors has already been installed, and these sensors have resolution capable of capturing the small variation that occur during the well test. In the oil field, the temperature data is usually used to estimate the formation temperature, the production of gas, and the leaking along the well. However, recent studies shows that the temperature transient can be used to better characterize the reservoir properties. And another important information is that the temperature sensor resolution is better than the pressure sensors. The main goal of this work is to deploy a new pressure and temperature analysis methodology for estimating reservoir parameters. For this, we upgrade our flow simulator to consider heterogeneous permeability in the fluid properties with pressure and temperature dependence. For the validation, we are comparing with different cases running our flow simulator and with a commercial software, and for the inverse problem, we apply the SMD method. In practice, the first part of the project want to simulate a cylindrical reservoir coupled with well-born with heterogeneous permeability near the well to provide the pressure and temperature transient data. To simulate the field data, the noise was introduced in those simulated data. Given this noise data, we'll solve the second part of the project. For this, the SMD method is applied to estimate the values of the permeability of the different regions and the porosity, making a history matching with the pressure or the temperature data. The first part of the project is the direct problem, in which some assumptions are considered. For example, the model considers a cylindrical single-layer reservoir with a single-phase flow. The fluids are slightly compressible and miscible. The flow is governed by the Darcy's law, and the reservoir is non-homogeneous, and the well is fully open through the entire reservoir thickness. To solve the directed problem, a finite code was developed in MATLAB to solve the mass and energy conservation through the reservoir, the mass, momentum, and energy conservation through the well. Instead, we have some terms that some authors do not consider in order to simplify to solve analytical problems. The second part of the project is an inverse problem. For it, a non-deterministic method was adopted to give a range of values as response. The commonly used methods are the ensemble common filter and the ensemble smoother with multiple data simulation. The ensemble common filter is an adaptation of common filter to solve nonlinear problems, while the ensemble smoother with multiple data simulation is an adaptation to transform the ensemble smoother in an iterative method. Here we have some applications of those methods in nonlinear problems. All of those methods are interesting to obtain the maximum posterior estimate, the MAP. But to understand the MAP, some theoretical explanation is necessary. First of all, the hierarchical relationship between the data and the model can be represented by D, where D is the response of the simulator when introducing a vector of parameters M. To simulate a real field data, a Gaussian noise was introduced to create observed data DOBS. The conditional probability density function means the probability of measuring an observed data given a model of variables M. The coefficients of the exponential came from the regularization between the observed data and the calculated data. And consider that then the prior model variables initially uncertain. The prior uncertain can be described by those equations where the regularizations between the model and the prior estimate of the variables. But to solve the inverse problem is necessary the opposite. It's necessary to obtain the probability of measuring a model given an observed data. For this, the Bayes theorem can be applied in originating our objective function. Oliver and Reynolds evaluate the ACN of the objective function and show that for linear problems, the ACN is positive definitely and has a unique global minimum. The map will be the parameters that minimize the gradient of the objective function for linear problems and has this formation formula. To decide which method would be applied, we use the American Reynolds work in which a high nonlinear problem was solved with different ensemble methods, and the SMDA presented the better cost benefit. And how the SMDA update process is done. Here is a dynamical schedule of the update process. We have the prior estimate, and as the simulations occur, the prior data get closer to the observed values. The sequence of this schedule is obtained using this update formula. This formula came from the formulation of the map shown in the previous slide and taking account the prior parameters and the relationship between the observed and the calculated data. The first results are the validation of the in-house flow simulator. The sand phase pressure and temperature was validated with the commercial software using Newton Synapse properties. And for the wellhead temperature was used the property from Mauricio Galvão. Now we'll be present the inverse problem result. For this, the in-house code was used to simulate the reservoir with skin or damage formation. The skin could be a natural effect during the oil production, and as a consequence, the permeability near the well reduces or may be increased by inductive process. As mentioned before, a Gaussian noise was introduced into the wellhead pressure of approximately 1 bar and 0.06 Kelvin to the sand phase temperature. The fluids and the well properties were taken from Mauricio Galvão works. For the analysis, an ensemble of 100 individuals was used, where each individual is a set of permeability and porosity values. 4 simulations were performed as commonly used in literature, and another important parameter for the method is the covariance matrix measurement CD that were set 10 times the maximum amplitude of the noise. To evaluate the result, 10 experiment was used to create 10 different starts in the ensemble. In the graph, we have the result of the history matching for the pressure and the temperature data in blue, and the response for the initial population for all experiments in gray. As we can see, the pressure results obtained a better data match, but it was to be expected since there is information literature about the parameter used. Although the temperature data match were not good as the pressure, but they were also significantly. Now is present the box plot of each variable for all experiments considering the pressure as an observed data. The range of permeability were not large, and the median were close to the expected value. As we can see, the biggest error was approximately 6% of permeability, and the porosity was the variable that stayed away from the expected with 14.5% of error. Now, the box plot for the temperature data as an observed data. The range of values were much higher than the pressure, but the median of the box plot represented by this red dashed line was closer to the expected value. As you can see, the biggest error was approximately 4% for the permeability and 17% for the porosity. As a conclusion, we have the implementation and validation of the 1D numerical model considering an isothermal flow, the successful implementation of the SMD method, and the parameter estimation using the pressure and temperature data. As future work, we are doing a parametric analysis of the SMD method, and in order to increase the parameters number, we are evaluating the investigation radius of the pressure and temperature data. Finally, I would like to thank everyone for the attention and acknowledge for those institutes for the financial support.